Good morning, champs. Today we are going to understand why we replace a distributed load with an equivalent force when calculating internal forces. Consider a cantilever beam that is 4 meters long and carries a uniform distributed load of 3 kilonewtons per meter. We measure the coordinate x from the free end toward the wall, so x increases from right to left. Our goal is to determine the internal axial force, N of x, the shear force V of x, and the bending moment M of x throughout the beam. After we cut the beam, the isolated free body would contain infinitely many tiny load forces. We could, in principle, add all of them individually, but that would make the equilibrium equations unnecessarily complicated. Instead, we replace the distributed load with one equivalent concentrated force. Equivalent means that the concentrated force has the same total force and produces the same moment as the original distributed load. As the cut moves toward the wall, the isolated beam segment becomes longer, so more distributed load is included. For a cut 1 meter from the free end, the equivalent force is the load intensity multiplied by 1 meter. For a cut 2 meters from the free end, it is the load intensity multiplied by 2 meters. For a cut 3 meters from the free end, it is the load intensity multiplied by 3 meters. In general, the equivalent force equals the load intensity multiplied by the loaded length. We now define our sign convention. We keep the right-hand segment of the beam. On the right cut face, positive axial force points to the left, positive shear force points upward, and positive bending moment acts clockwise. Other conventions are also correct, but the arrows, equations, and diagrams must always remain consistent with the convention chosen. We begin with the axial force. There are no horizontal external loads acting on the isolated segment. Therefore, horizontal equilibrium immediately tells us that the axial force is zero everywhere. Next, we determine the shear force. The equivalent force acts downward, while our positive shear force points upward. Applying vertical equilibrium gives the shear force equal to the equivalent force. Since the equivalent force equals the load intensity multiplied by x, the shear force also equals the load intensity multiplied by x. Substituting the numerical value gives the shear force equal to 3x kilonewtons. At the free end, where x is 0, the shear force is 0. At the wall, where x is 4 meters, the shear force reaches 12 kilonewtons. The shear force diagram is a straight line, increasing linearly from 0 at the free end to 12 kilonewtons at the wall. Now we determine the bending moment. The equivalent force acts at the center of the loaded segment, which is located half of x from the cut. We defined clockwise moments as positive. The assumed internal bending moment is clockwise, and the equivalent force also produces a clockwise moment about the cut. Therefore, both terms enter the equilibrium equation with the same sign. Solving the equation gives the bending moment equal to negative 1/2 times the load intensity times x squared. Substituting the numerical value gives negative 1.5 x squared kilonewton meters. At the free end, the bending moment is 0. At the wall, it reaches negative 24 kilonewton meters. The negative sign simply tells us that the actual bending moment acts opposite to the positive direction we assumed. The bending moment diagram is a parabola, changing from 0 at the free end to negative 24 kilonewton meters at the wall. Notice the pattern that appears. A constant distributed load produces a linear shear force function. A linear shear force function produces a quadratic bending moment function. Every time we integrate, the power of x increases by 1. The same procedure also works for triangular loads, trapezoidal loads, and even arbitrary load functions. The only thing that changes is the expression for the equivalent force. Finally, our coordinate direction and sign convention lead to 3 very important relationships. The rate of change of the shear force equals the distributed load. the rate of change of the bending moment equals the negative of the shear force, and the second derivative of the bending moment equals the negative of the distributed load. The main lesson is that the equivalent force is not just a shortcut. It is the bridge between a continuously distributed load and the equilibrium equations. As the cut moves, the amount of included load changes. That is why the equivalent force, the shear force, and the bending moment all become functions of position.